Thank you again for this opportunity to present the SRN tool, and welcome to everyone to this August gathering of people who are here to look at our demonstration of the SRN tool. As Catherine mentioned, we are trying to uh, do this once in a month. So as we start this presentation, allow me to draw this inference as I'm making this presentation here today. Australia is gearing up for what is supposed to be a cyclone that hasn't happened for the past 3 decades now. A cyclone Alfred that's coming towards the coastlines, and it's supposed to hit sometime tomorrow or day after tomorrow. Now, the point I'm trying to make here is that with any kind of disturbance that happens, the importance of any kind of a modeling and simulation based tool, importance of any kind of a digital tool that allows us to understand, pictorially understand what the real time event is looking like, is an extremely important aspect. With tools that for humans, for tools such as these, which predicts the extreme weather events or which predicts how the movement of cyclone is happening and things like that, it allows us to respond immediately to any kind of threat. It allows us to prepare and save the communities as and when required for in preparation of what is about to strike. But what about marine mammals? What about coastal communities? What about other communities that live near the seashore, and the problems that have been happening? It's not something that is immediate, but something that has been gathering for over decades and decades of time. Uh, every day, shipping traffic contributes to a rising underwater noise. Footprints that are disrupting our marine ecosystems, interfering with our communications among species, and even altering all the migratory patterns that are happening in the species. Now, the article on the left essentially is a stark contrast. This is an old article again from 2016, where more than 80 whales have beached on India's southern coast. And a lot of it is unknown, a lot of information about it is unknown as to what has caused this. But noise, a huge amount of noise pollution has definitely contributed to this, because when there's an increase in noise, these marine mammals cannot communicate with each other. They lose their ability to communicate because, again, sound is the only way for them to communicate. Light does not propagate underwater. So therefore, it is extremely important for us to have a similar tool, similar set of modeling and simulation based approaches that allow us to identify the changes that are happening to a habitat in real time. And the shipping noise, the low frequency, the shipping noise is predominantly uh, the most impacting noise at a low frequency range of 100 hertz to 500 hertz, and that is the same frequency range in which the marine mammals communicate, in the same frequency range in which most of our equipments operate, and so on. So therefore, it's extremely important to understand what we are actually looking towards. Now, ideally, when we look at any kind of traffic, when we look at the shipping traffic in Indian Ocean region, from an economic perspective, from a blue economic perspective, we kind of feel safe, and we feel pride in the aspect that the kind of shipping lane that we are forming. It's Indian Ocean region today is one of the most important sea areas globally. It is the focal point of both the maritime trade. It's a geopolitical hotspot, and most of the shipping traffic, international shipping traffic, does flow through this region, and that provides a massive boost to the economy. But then the picture that I'm showing here, sorry, the picture that I'm showing here, being generated from the tool that again Jay will be demonstrating, uh, showcases the alter side of it, in which the amount of noise that we are generating in the region because of this ship. So these yellow dots that you can see here are basically the ships that are moving in the region, and the color coded map represents the noise level in dB reference 1 micropascal. Um, so the problem statement is very clear. There is a huge amount of shipping traffic in the region. We'll talk a bit more about it's what kind of disruptions it is causing. But in terms of the existing methodologies, existing solutions that we rely on, most of these solutions are uh, estimation of cumulative long-term noise. What I mean by that is that we do not have a feasible solution, an economically viable solution that allows us to estimate the noise that is happening in real time. And therefore, that it basically fails to capture any kind of fluctuations that happen in the noise, and how the marine ecosystem will get impacted, how the naval operations will get impacted, and so on. So the point here is clear. The ocean is no longer silent, and all the existing methods that we have is not enough to deal with real-time challenges, and especially so for developing countries. As I mentioned, we have to also consider the economic aspect, that whether a solution can actually be truly deployable or not. And that's where this modeling and simulation based approach comes into picture. Now we'll talk about why we are going with why the existing solutions tackle more on cumulative and we are looking at instantaneous and what has actually helped us reach that goal. But just to give a bit of a glance of how the existing noise levels compare. Uh, Today, using the tool again, today we saw that the total noise level at a frequency range of 50 hertz is clearly around 120 to 130 decibel that we are getting. Now, 130 decibel is a huge amount of noise. That is basically almost we are in the borderline of exceeding the safe threshold for marine species. And when we look at higher frequencies, 100 hertz and 200 hertz, this noise level increases more and more. Uh, but the point I'm trying to make is that this is the correct point. This is the right time that we need to be able to understand and we need to be able to perform actions, take policies as we grow into the future. Now, this is not an immediate problem. This has been happening for decades. G.V. Frisk, around 10 years ago, in his paper, has established that at every decade there is a 3 decibel increase in the noise level. But the pattern that we are seeing is much more than that. And there is a significant reason for it because as we grow, with the rising years, the kind of shipping, the kind of technology that we're using is increasing. The size of the container has doubled up. The kind of weight that a container can take up has doubled up. The propeller cavitation noise that is being generated is much more today as compared to what it was earlier. So there are a lot of factors that contribute towards this increase in the shipping traffic, and no one single model, like no mathematical model that we establish. So similar to any mathematical model that was established during the Cold War period, that has been the base during the Cold War. An acoustician named Donald Ross is the one who created. He basically grabbed the noise recordings from sushus and he then created a mathematical model that allows us to identify the shipping noise or noise level from a single emerged from a single ship using its properties, length of the ship, speed of the ship, and so on. However, with an exponential rise in the shipping traffic and the shipping noise, mathematical models do not cut mathematical existing mathematical or equational models do not cut out for noise estimation. And that is where we have integrated a lot of artificial intelligence into our tool, and I'll talk a bit more about that. Now that we understand the problem, what is the motivation? Like, okay, fine, we'll solve the problem. What are we really trying to achieve here? Now, first and foremost, fuel and route optimization. Now, an increase in the shipping noise, so being able to monitor what is the noise that is being generated by a ship in real time will essentially tell the shipping industries will help them identify which are the vessels that needs more maintenance. Because an increased noise, which essentially means that there is a huge amount of drag and the engine is inefficient, and all of those factors basically increase operational cost. So identifying well before time what are the vessels that needs any kind of maintenance is an extremely important aspect. Environmental impact assessment is again an important factor. Most of the projects that we do, especially in the maritime domain, that involves establishing of shipping lane, establishing of ports. In fact, my able colleague Catherine also recently did a research work where she analyzed uh, the fact that most of the port construction, while we are considering the impact that is being generated, with the noise impact that is being generated, we are not considering the wider impact in terms of the marine organisms in the place. What kind of habitat are we destroying? It's essentially just in terms of what kind of noise level will reach the shore, not in terms of how the habitat is getting destructed and so on. Any kind of naval equipment, any kind of submarine, let it be operation of sonar, submarine stealth planning, everything requires us to have a approximately good enough signal to noise ratio mapping, which tells us what kind of noise level is in the region. Because the more the noise level, the more difficult it is for the sonars to operate. The efficiency of those equipments will reduce further and further. IMO is tightening its regulations. Now IMO has released a glow noise project that we are also participating in. But this will basically put us on map, allowing us to propagate further and abide by those rules and those tightening regulations that we have. And in terms of the monetary aspect, now we have seen that sustainability has been a topic of talks for a lot of time now. It's been almost around a decade that people are talking about how can things be more sustainable, and industries are pouring more and more money to reduce their carbon footprint and so on. So having a tool that basically lets a port analyze what kind of noise is coming towards their port, what kind of each ship that is coming to the airport, what kind of noise are they generating, will essentially allow them to optimize the docking and prevent any kind of noise hotspots that is being generated near the region. So basically, more promoting more of an eco-conscious business. And of course, protecting marine habitat is something that is always there. That is the primary aspect. But I also wanted to bring out the other factors into picture. Now, when I said about the ports being able to identify the kind of shipping traffic in the region and so on, so this is a glimpse of the tool here again, where you can see that as a user can hover over a particular vessel, it basically shows the noise being generated by that particular vessel, the vessel details, what is the name, MMSI, the speed that with which the vessels are moving, and so on. And of course, the color-coded ship details. So this is not ambient noise map. This is just the noise that is generated from the ship's propeller, which basically showcase the color codes basically showcase that the darker vessels are having higher noise levels and the lighter vessels are having the lower noise levels. Now this architecture that Sir showed a glimpse of, I'll expand a bit on that. Now it's not easy for any kind of a tool generation when we talk about ship noise map, real-time estimation of shipping noise, and there is a reason why it has been a difficult venture for many people, in the past. The reason for that essentially is that so estimation of shipping noise requires a lot of information. It requires the data about so we collect the data about the bathymetry, the temperature, salinity, sediment, all about the ocean properties that are required for estimation of the sound speed profile, which basically tells us how a signal is supposed to propagate in the water, how much reflections is going to happen, how much refraction is going to happen. We also consider the seabed attenuation, how much, depending upon the type of sediment, the attenuation that is generated by the seabed is different. So we consider that and we feed all of that into acoustic propagation model. Now, in terms of acoustic propagation model, again, there are various models, which basically depends upon which location you belong to. Whether so, as I mentioned, the tropical aspect of the region. Uh, for regions where we are, so even though Indian Ocean region is deeper in terms of the depth, the fact that we have a high temperature in the surface, which basically means that up till at least 500 meters, 1 kilometers up till depth, the temperature never reaches a 0 degree gradient, which means that the signal, so up till that point of around 800 meters or below, uh, any kind of deployment, any kind of signal has a massive amount of attenuation that happens to that particular signal when we're talking about long range propagation. So therefore, it is important for us to identify the right kind of model. Now, I'll come back to this. This is an important bit that we have integrated into the tool. And we have not used, so PRAM model is a base model that we have used, but that is not what our tool is actually using. Now, in terms of AIs, again, we basically used we created an API that talks to Spire and that essentially gathers real-time AIS data, much like what marine traffic or any other kind of tool provides. It gathers real-time AIS data, what is happening in that current spot. And then, of course, we have a lot of error detection and correction that happen in that particular data, some pre-processing. And then we use the most advanced model, which is a Vatican model for estimating the noise that is being generated from the ship. So when I say Vatican model, what's actually happening here is that, so as I mentioned earlier in the Cold War period, Donald Ross created a model using length and the speed of the ship. What we are doing now is that we have divided the sound into 3 different profiles, and depending upon the speed with which the ship is moving, if it is moving below the propeller cavitation threshold, then we consider the engine noise that is being generated by the ship. So again, we need engine parameters of the ship, the number of engines, the block coefficient, and so on. And then if it is moving at an increased pace, which is exceeding the propeller cavitation inception speed, so that essentially means that the noise that is generated by the propeller is basically overtaking the overall noise of the ship, and therefore then we calculate the noise of the propeller of the ship. So we have a model that basically differentiates between the two and identifies the noise being generated by the ship, and all of that is what is being fed into our noise map. Now, as we move forward, now the tool that we have generated, again, we always talk about to see, to understand, and to share. It is extremely important for us to have any kind of tool that is deployable in multiple devices so that it is much more usable and it is much more user friendly. Creating a tool that basically needs to be running on a user's high computation machine wouldn't really be, again, a viable solution. So we wanted a solution which allows us to run it on cloud so that as a user, you just have to select a region, you have to drag a region for which you're interested in obtaining the noise map for, and the tool will essentially provide you the noise map for the region. And all the computation, everything happens on the cloud, which basically means that the data gets stored, it gets cached so that it can be fed on multiple instances. We have a historical data that we record if you want to go back and identify, or you want to perform some analysis on there. And again, based upon where you are at, what device you're using, we support a plethora of devices, both the large breakpoints, computers, as well as handheld devices such as mobile and tablets. Now, no, so as I move forward towards the features, there are two key components that has basically helped us achieve the kind of performance that we are gathering for. The first feature is H3 indexing. This is a technology that is developed by Uber. So what that essentially means is that we use hexagonal spatial geospatial mapping for mapping purposes. Now, this is different from any kind of a grid-like system that we usually have, because it essentially means that there is a standardized global coverage that we have. So to give an example, a hexagon having a certain unique ID is the same across any kind of place in the earth. So it doesn't matter if I map it in my tool or some other tool. If I just go to an Uber's let's say interface and see what is the ID for that particular hexagon, it is the same. So the point I'm trying to make is that that standardized approach allows us to expand. So right now this tool is centric to just the Indian Ocean region, but then we are planning to expand a bit more on that as well. So a hexagonal approach allows us to expand. Now, hexagons have an increased spatial resolution, which means that it allows for fine-grained modeling and noise distribution across the ocean. Um, because of the fact that these hexagons are pre-computed, we don't really have to go about identifying which grid the noise is coming from, and all the noise propagation and everything we are able to directly map to each of the single hexagons and therefore perform the mapping. Now, in terms of the last key feature, again, as I mentioned, we have integration with multiple vessel systems, marine traffic data last expire. So we have the capability of automatically ingestion of AIS data. So all these external vendors we can support. And at the same time, if for some reason we feel that the user feels that they need to upload an AIS data manually and they don't want to use an automatic AIS data for any kind of operation, let's say a naval operation mechanism a naval group wants to upload their own AIS data, we have the feasibility for that as well. Now, let me help you. Let me try to backtrack a bit in terms of coming back to the whole ship noise generate mapping aspect. Now, not going into too much amount of details, just to quickly showcase the methodology about it, or basically tell about the methodology about it. So what we have done to estimate the noise that is generated in the region is that we have divided the whole region into small grids. Those grids are basically being formed by hexagons. And at the center of each grid is the receiver point. And from each receiver point, we basically calculate a radius of 200 kilometers. And any kind of ship that is falling within the 200-kilometer radius, we calculate the noise from the ship and what is the impact of the noise generated from the ship on that particular receiver point. And with the 200 kilometers, because 200 kilometers is like no noise and no signal strength in Indian Ocean region goes beyond the 200 kilometers of range. And therefore, that's the range that we have considered. So as we estimate the noise, uh, for each ship, we identify that what is the ship type, what is the propeller noise that is being generated, what is the engine noise being generated, and all of this is happening in real time. So just to give you an understanding of how much computational power goes into it. However, it is also important to understand that it's not so. Most of the existing solutions that we have essentially uses most of the existing solutions that we have today uses empirical models to solve these kind of problems, which is the estimation of transmission loss. So what I talked about the ship and the receiver, then when the noise propagates from the ship to the receiver, how much transmission loss is happening between them is something that is computed empirically. However, and this is work that we have done just a few years ago, we wanted to identify an approach which allows us to perform real-time estimation, which means that we cannot have a model. So with the empirical models, for if you can imagine, for every ship and receiver pair, if it's going to take 10 seconds to compute the transmission loss, you multiply that by thousands and 10,000s of ships and receiver pairs. So we are talking about something called as an order of n computational complexity, which means that as the number of ship and receiver pairs increases, so does the computational complexity. And that is what the existing PyRAM model that I showed you had. What we went ahead and did was we basically created a neural network which basically performs a real-time estimation of transmission loss. So instead of using a mathematical model, again, we constructed a neural network around it, which will predict the transmission loss for the given region. So this neural network is trained only for the Arabian Sea, Bay of Bengal, and the southern Iowa, the exact area that we have used right now. And the image that you can see on the bottom right is the computational efficiency, the amount of time taken. So although this looks like a very artificially made graph, it is not so. So the time complexity, as you can see, for 1,000 sender receiver pairs with a neural network was nearly 2 seconds, as compared to with a existing PyRAM model, the mathematical model was close to 160 seconds. So that's the kind of drop in execution time that we have achieved using this neural network. And as you can see from the graph on the bottom left here, there are some, obviously there will always be a room for error. So we are considering some plus minus 5% of error rate here. And as you can see, most of the spread is within that category of plus minus 5%. So plus minus 20 decibels of transmission loss that we are getting. But majority 85% of the data that we considered is falling within the acceptable range. In terms of, it's important for us to also validate our work. We had a recording made from off the coast of Goa, and what we had basically done was essentially we basically place our work on top of the real recording that we have. So as you can see, our work, we are very close to the real recording. Again, a plus minus 5 decibel, plus minus 5%, 10% in values is acceptable range, and that is what we're aiming for. So we did compromise a very small 5% in accuracy, but then we gained a massive amount of advantage in terms of reducing the computational complexity of the algorithm. So moving forward, I just wanted to provide a sneak peek. Marine spatial planning that Catherine mentioned, this is what we are aiming for. This is what we are integrating it towards. In the broader picture, we want to create a tool which accumulates all kinds of different information in a single place. That basically means that right from climate change risk management to resource mapping, understanding where is snapping shrimp, where are the oil rigs in the place, if there is an oil leakage happening, where is it happening. Every map, every MSP tool that we have can showcase the AIS data or the shipping traffic in the region, but we want to go a step beyond, and we want to also showcase what is the useful information that we can derive from that particular data, because that is more valuable to the policymakers for constructive policy building. And that's where that's our aim behind creating this MSP tool, and that is why we are aiming towards the ship noise estimation and so on. So for each of the data that we have, the wind, the shipping traffic, the oil rigs, we will be extracting useful information out of it, and we'll be integrating that into the planning tool. So in terms of the future, we are essentially looking at an expansion of AI-driven monitoring system. We are looking at integrating of cloud-based UDA platforms. The sustainable policies is something that we're aiming to be adopted by the governments, and any kind of broader project, any kind of massive project requires a community-driven approach. Anything that requires that the people on ground. So we have people. We had the team go to different coastal communities in Gujarat and Maharashtra and other places, and we have interacted with those people, and we want support from such kind of coastal communities who can perform data collection, who can participate in this particular initiative. So as I end my presentation, now, of course, it is engineers definitely develop the tool, but then I feel that it is every stakeholder is extremely important for us. Every person in the team is extremely important for us. This initiative has been, from an engineering perspective, this initiative has been led by Jay, and he'll be making the demonstration next. But then every single person that you can see in the picture is extremely crucial, and they are the ones who have helped us through this initiative. This has not been a easy challenge for us. This is something that we have been working for the past 5 years or more than 5 years to begin with. But then we are very happy to see close to completion for this particular initiative. And with that, I stop my presentation here, and I request Jay to make the demonstration.